So when we look at this, and remember there's two altitudes for every parallelogram. One of them for this parallelogram would be either there or there. Okay. Now the other one would be maybe, and I'm just kind of guessing here, I can make it right angle, maybe like that. Does that kind of make sense? It'd actually probably be maybe further down. There. It might even be, depending on the severity of this, the other altitude might even be, it looks like it's more like that one. Does that make sense? Would you think about finding that altitude first? No, that's going to be a huge undertaking to find the length of that altitude from what we're provided here. It's doable, but it's going to be pretty involved. Okay. What you'd have to do there, you take the 13 up there. You don't know this distance here, so maybe you call that X. And you go through, this is 52. You go through some SOHCAHTOA stuff, and maybe you can find it. Okay. You would be able to find X using cosine here, and then once you find that, maybe use Pythagorean theorem to find this distance. It's going to be a nightmare to do that. Okay. Wouldn't it make more sense? And this is another key for us. When they give me this angle here, it probably makes sense to focus on using that angle of 52, right? Now, the angle of 52, I know it's kind of hard to sometimes just creating these things and put them in the spots the sizes of the parallelograms they give me. But 52, remember, is that angle right there. Okay? How can I find H? Why would you use sine? I agree with it. Okay, and you know the hypotenuse to be what in this case? You know that 6 right there is the same as that 6. So if we got this being the opposite side, and this is the hypotenuse, we'll say sine of 52 is equal to opposite over hypotenuse. So H ends up being 6 sine of 52. So what's your base going to be? If that's the H that we use, what's your base? 13. So we go 13 times 6 times sine 52. You've got really three numbers being multiplied together here. Okay. Remember, sine of 52 is a symbol for another number. Okay. Sine of 52 is going to be a number probably a little bit bigger than 0.7, a little bit smaller than 0.8 maybe. Okay. But it's a number regardless, but it's an irrational number. Okay, so if I look at those three numbers up there, so basically what we've got, let's actually write this out on Desmos real quick, because the question asks you to leave it as an exact answer. So if I'm on Desmos, and I ask this thing to find sine of 52, okay, there's the 0.788 that I was talking about, okay? Just want to make sure I'm in the right mode. I should be, degrees, yep. So right now what we really have here is 13 times 6 times this number 0.788 that keeps going on forever, right? And never repeating. Which of those two of those three numbers operate best together? 13 and 6. So what we'll do is we'll multiply those together, and that gives us 78. Okay? So what I'm trying to get at here is basically identifying the numbers that are rational, combine those, doing the operations that are present. So 13 and 6 will be multiplied together, gives me 78. And then I have times sine of 52. Remember, this is a rational number times an irrational. We usually, if we want an exact answer, that's the way we have to do it. Okay? There's no other way of doing it, other than maybe using, because we know sine and cosine are complementary. I could say 78 cosine of 38 would give me the same result here. But that's the most direct way of writing the exact answer. Does that make sense? Okay. Now, if I asked you, okay, well then you go to Menards and you buy some topsoil or mulch or whatever that is going to cover that area maybe 2 inches deep. Would you go to Menards and tell a guy that's working there that you've got an area of that much? No. Okay. So you would, depending on the application, then take this and write it as 78 sine of 52 is that right there. Okay, so this is the exact answer. This is rounded. Okay. Now the nice thing about this is that it's rounded right there. Okay, we know the 1 that is before that 3 is exactly 1. But I don't know if that 3 is truly a 3. Okay, it could be a 3 because the number after it was less than 5. Okay, or that 3 could be a 2, and the number after that 2 was actually a 5 that the calculator now rounded that 2 up to a 3. Okay, so when you type an exact answer into Desmos or whatever calculator it may be, that last number that it presents you is not precise. You are, let me rephrase it this way, you are uncertain about that precision because you don't know what the number after that has made that number do. Okay, it should either be a 3 or it should be less than that by 1. So it should be either a 3 or 2. Some programs, I used to have one, but since the whole virus thing, my program disappeared and I can't get it back, and I have to pay for subscription and stuff like that. It's kind of a pain, but it would show. I could type in that number and it could show me however many decimal places I requested. I think up to like 100 million decimal places, something like that. It's kind of crazy, but most of your calculators will go 10 decimal places. Some go 15. But when we need that, if for our applications, we're never going to need to be that precise. When they ask us to go to a decimal place, we'll always go 2 places or 3 places. And in real life application, that's probably going to be far enough as well. So all your calculators will be fine. So that was 5. Any others? 7, both parts of 7? Okay, what kind of trapezoid is number 7? This first one. Yes, there is. Yes, we did. Not equiangular. Not equilateral. Isosceles. If you go through enough of them, you'll get them. So that's isosceles because the legs are the same length, right? If you were to extend those 5s upward, okay, they would eventually intersect at another vertex, right? An intersection point. And what would that triangle be? That would be an isosceles triangle. Okay. So here we've got this trapezoid we're trying to find the area for. Area formula for a trapezoid, 1/2 h times the sum of the bases, right? Okay. Now, we've got the sum of the bases. Sum of the bases is what? 18, right? 6 plus 12. How can I find that distance right there? Any ideas? And it has to do with how we ended up creating this formula in the first place. Does anybody remember what shape that formula actually comes from? Nope. Nope. That formula came from the area formula of a rectangle. This comes from just B times H. Okay, I think that was maybe Wednesday's introduction to the class. Would you agree that that is also H? Okay. Now, when we draw altitudes, okay, not only are they perpendicular to this side, okay, so altitudes from triangles go from a vertex perpendicular opposite side, right? Altitudes of quadrilaterals parallelograms, trapezoids, that kind of thing, they start at one side, go perpendicular to the other. But what that does at that starting point, because that's parallel to that, that means that angle has to be the same as these angles down here. So that's got to be a right angle. Does that make sense? This has also got to be a right angle. So what kind of shape then do we have here in the middle? We have a rectangle. If you have a rectangle, what would be the length of that distance right there? That'd be 6. So what would be the length then of that distance right there? It'd be 3, right? Does that make sense to everybody? Because this triangle here is going to be congruent to this triangle over here. So 3 plus 6 plus 3 gives me 12 again, right? Why does that allow me to find h over here? Pythagorean theorem now. So h is going to be, if my hypotenuse is 5 and I got one side to be 3, does anybody remember what the other has to be? 4. Pythagorean theorem tells me 3 squared plus h squared equals 5 squared. That will give me h squared equals 16 eventually, h being 4. So we go 1/2, 4 times 18. Does that give you 36? Good. All right, so that was the first one on number 7. This one's no different. Okay? Still going to use the same formula. Now, just the way that we come across those values for h, maybe we have to use different tools other than the Pythagorean theorem. Okay? This is no longer an isosceles trapezoid. Isosceles trapezoids, these base angles are the same. Okay? Over here, we're seeing our base angles are not the same, so this is not isosceles. So what we're going to do is we're try to navigate through this to figure out area equals 1/2 h b1 plus b2. Now, you have one of those bases. You have base 1 maybe being 14, right? I don't know what base 2 is. Base 2 is at least 37 units long. Would you guys agree with that? We've got that a little bit in that 30, 60, 90 triangle that we don't know. Okay? So, here's my question. Do you know anything about this triangle right here? Okay, you know that's 30 degrees. That's a 30, 60, 90, right? So you've got the angle measurements, but do you have any sides that can work in tandem with those 30, 60, 90 relationships to move around and find distances? Because we got to find that dotted line, right? That's h. And we got to find this solid segment right here because that's going to help me find B1 or B2. Okay, I can subtract 37 and 14. And when I subtract 37 and 14, doesn't that give me something over here in this triangle? Okay, so when I subtract those, what's that give me? Okay, so it gives me 23, which then turns into this distance right here, correct? From there to there. Is that all right with everybody? That's 23. What kind of triangle is this yellow triangle? 45, 45, 90. So, what is that distance? 23. And what was that in our formula? That's the height. Still don't know what base 2 is. Okay? So, this 23, can that be transferred over here to be in that distance? Okay, so what is that in a 30, 60, 90 triangle? Is that in 2n or in radical 3? It's just n. Okay, so what's across from 60 then? Should be in radical 3, right? So 23 radical 3. Okay, now this was done intentionally because that distance is bigger than 23, But visually, the image does not show that, right? Okay, it looks shorter than the 23. But I did that intentionally to make sure that we weren't trying to do anything that was based on looks. Okay, I want to make sure our math is what we're making our decisions on. So now, how can I write this distance here, which we're calling base 2, how can I write that using these two things? 37 plus 23 radical 3. Can I combine any of that stuff? No. The only way I can combine radicals is if the radicands are the same. So right now that 37 has a radical 1 on it. We don't usually write it, but you can. And then that 23 is a radicand of 3. So those two things have to be the same in order for us to merge the coefficients out front. Okay? So they're different, so we can't merge them. So base 2, when I rewrite my formula here, we got 1/2, 23, okay? We got 14 plus base 2, which is 37 plus 23 radical 3. Okay? Now, that is fine. If we're only interested in like getting the area to the nearest tenths place, hundredths place, thousandths place, we could type that into Desmos, TI, whatever it may be, whatever calculator we want, hit enter, and the calculator will do all the order of operations for us and will be out to 9 decimal places, be 100% accurate with our answer. Okay? However, if I want to write it as an exact answer, an exact simplified answer, that's not good enough. Okay? So what we need to do is we need to go through our order of operations and we need to start simplifying. Okay? So order of operations starts with parentheses, right? So you need to go inside all your sets of parentheses and basically restart your order of operations again. So I'm going to look inside this set of parentheses first. Okay, 14 plus 37. Those are my two numbers that I can add together because those are rational. So what's 14 plus 37? 51. So I have 51 plus 23 radical 3s times my 1/2 times 23. Okay, so this is fully simplified using my addition rules. Obviously, there's nothing inside these parentheses here that we can do. So now the next thing is to multiply, right? Okay. Now you got some options. You can either multiply those two things together first, or you can multiply these two things together first, or you can multiply those two things together first. Those are your options. It's the commutative property of multiplication, right? I don't think one technique, one route is going to be any easier than the other with these numbers because they're odd values, and no odd value works real well with a half, right? So what I'm going to do is I'm going to multiply those two together. So when I multiply those two together, what does that mean? What does that notation mean I have to do if I've got a number out here multiplied by a quantity? What do I have to do with that 23? I need to distribute. I need to take 23 times 51, and then 23 times 23 radical 3. So 23 times 51 is 1173, and then 23 times 23 radical 3 ends up being 529 radical 3. That's all then times 1/2. Does it make sense? What do I need to do with that 1/2 then? It's the same as it was up here in blue, wasn't it? Same image. I need to distribute. So take that 1/2 and distribute. So we get 1173 over 2 plus 529 radical 3 over 2. And that would be a fine answer. Nothing wrong with that. But do you have a common denominator here right now? So a lot of people might write that as 1173 plus 529 radical 3 all over 2. Kind of a nasty problem, yes? Okay, lots of stuff going on there. Lots of 30, 60, 90 triangle, 45, 45, 90 triangle. Transferring distances, okay? Understanding relationships that white figure up there in the picture is a rectangle. And opposite sides of rectangles are congruent. Allows you then to transfer distances, okay? Using the segment addition postulate there. And that's just the geometry. Then on top of that, you have to have some pretty good skills with your algebra to get that in a nice, concise, final, exact answer. And that I like. You know, students don't usually prefer this, but I like the fourth 9 weeks in a geometry and in all my math classes because it's a culmination usually of everything you've done so far in the year, and you start to see everything kind of coming together, everything being used from different corners of the course to accomplish one obstacle. Okay, so we got a lot of stuff going on there, but it gives you kind of insight to how mathematics builds on itself. Okay. Any others? I do not have the answers to them, but we can. To 4. So 45 sides of 6, so 3 radical 2. Is that 30 radical 2? Number 4, 30 radical 2. So if we've got a 45-degree angle here, this side is 6, right? So that's your n radical 2 side. So divided by radical 2, that will end up giving me this to be 3 radical 2. Correct? The base that's being drawn to then, that they provide, I've already used the 6 as the side, and this is 10. So 3 radical 2 times 10 would be 30 radical 2. I'm trying to think. I don't know. I mean, maybe we'll see here. If I would have made this, because I don't know if the wording here could have messed people up. Let's say that this is 45, because I chose this to be 6. But that could, I mean, there's nothing saying that could have been 10. And I bring this down. So if that was 10, this side here would have been 6. This would have been 5 radical 2. Doesn't matter. What's 5 radical 2 times 6? Still 30 radical 2, right? So when I tell you, so I don't need to give you a picture here when I say sides are 6 and 10. You could have made that 10 and this 6, or this 6 and that 10. It will impact what the size of the height or the altitude is, but the product is still going to be the same. Yeah. Number 6, find the area of rhombus with sides of 6, angle of 120. So you're going to get, so if I've got sides of 6, that means when we draw this through, okay, so the 120 gets split to be 60, right? This becomes 30. Sides of 6, so that's your 2n side, right? This would be then 3, and this would be 3 radical 3, correct? So what would one entire diagonal be? What would this entire diagonal right there be? 6. And what would this entire diagonal there be? 6 radical 3. So 6 times 6 is 36, times a half is 18, and times my radical 3. Question 3, I think, is something that maybe we should explore a little bit. It says a square is inscribed in a circle. Okay? Did anybody draw this picture here? Okay. Is the square inscribed in the circle there? No. If you drew that picture, you probably used either that distance or that distance, right? That is that the square is circumscribed around the circle, or the circle is inscribed in the square. Here it says, so when you read this, square is inscribed. So square is inscribed sounds a lot like inside, right? Okay, so the square is inside a circle, but the conditions of inscribe means that the vertices of our square touch our circle. Okay? So now, give me a description of what you would draw here to help you, because it says the radius is 7. So where are you going to draw your radius here? You're going to start there, right? That's where a radius has to start. But now, are you going to draw that radius? Why would you draw that radius? Yeah, but there's an infinite number you can draw. I could draw that one, right? I could draw that one. Okay, and all of those are 7. But what'd you say, Jagger? Why would you draw your radius to? You know, it could go to any one of the 4 vertices, but why would you draw it there? Okay, so that radius of the circle drawn there tells you something about your square, right? And we don't know. We're trying to find the area of the square, and we know nothing about it right now. Okay? So if I draw my radius there, that tells me it's 7, so the diagonal is what? Diagonal is 14. Okay, so we got a couple options here. Okay? What do you know a square, what's the area formula for a square? Side times side, right? Do you know your sides yet? Okay. But I know the diagonal. And what kind of triangle is that triangle right there? 45, 45, 90, or a right isosceles. Okay? So if the hypotenuse is 14, and that's your n radical 2 side, doesn't that make this side 7 radical 2? And that side right there is that side of your square, correct? So can I take 7 radical 2 squared and get then the area for my square? What's 7 squared? 49. What's radical 2 squared? 2. So what's 49 times 2? 49 times 2. Be 98, wouldn't it? What are we lost on? $14 squared is 196. So you took your hypotenuse and squared it. Let's do it this way. What shape is a square also classified as? It is a rectangle, so it'd be base times height, so it'd still be side times side, but it's a rhombus. So that formula should hold true. What's 1/2? Because if you're a person that used the diagonal and squared it, you should have gone actually 1/2 times 1/4 times, or 14 times 14. What's 14 times 14? 196. What's half of 196? 98. So you can use, because the shape classifies as other shapes, okay? And if we have formulas for other shapes, we can use those, okay? So if I ask you ever to find the area of a square, you have so many different ways you can do that. You can say, well, it's a square, so S times S. You could say it's a rectangle, so BH, which ultimately is still S times S. Just that when I use BH, B and H are the same value. You could use Because it's a parallelogram, you can use BH again. Because it's a rhombus, you can use 1/2 D1, D2. So there's a lot of different formulas that you can use to find the area of a square, because a square is classified or meets the classification of a lot of different shapes. Is that okay with everybody? I like that worksheet. You guys like it? No? Why don't you like it? Requires a little thinking, requires some effort. And I get when something doesn't make sense right away, you see struggle, a lot of people let that struggle be something that shuts them down, right? Let frustration, let that struggle be something that motivates you to get through it and to learn something from it. We'll stop with that stuff for now, but I want to pick up with, we're going to keep talking about area, but just introduce a new shape today, in which we're going to refer to area. It's not a new shape to us, but we haven't ever dealt with the area of these shapes yet, and they are regular polygons. And today, mainly, it's going to be a lot of just getting vocabulary out of the way so that we can really dive into it and dig into this stuff tomorrow with examples. You guys remember what a regular polygon is? What's a polygon? Okay, so it's a two-dimensional shape that each segment intersects exactly two other segments. There are no curves. Okay, it's closed. Okay, meaning that if you put something in it, it can't get out. And basically, we saw, if you remember back to chapter, I think it was chapter 6, we talked about this. We had an example, and I asked, well, that right there classifies as, or meets a lot of the characteristics or needs of something to qualify as a polygon, but that's considered not being closed. Additionally, polygons are going to, when we say they are closed, that means they're going to enclose an area. That thing would not have an area. Does that make sense? Okay. But what did the word regular mean to us? Anybody remember that? Because polygon, we could have a polygon, assume that all of those segments are all. Okay, so that's a polygon, but that would be an irregular polygon. Regular meant that they are equilateral and equiangular at the same time. Okay? So those are the types of shapes that we're talking about right now. Okay? Envision a stop sign. Stop sign is a regular octagon, regular polygon. Okay? We're going to try to find the area of one of those things. Okay? In order to do this, there's going to be some connections to circles, okay? And there's some vocabulary that we need to make sure that we're all understanding of and we use in a consistent manner. First one says center of a regular polygon. The center of a regular polygon is the center of the circumscribed circle, okay? So every regular polygon has a circle that goes around the outside of it that intersects each vertex of the polygon, okay? The center of that circle is identical to the center of our regular polygon. I'm going to bounce back and forth between GeoGebra here and the notes so you can see this stuff kind of in action. So if I let's just draw a regular polygon first. Let's just go with, we'll go with 7 sides, okay? So a 7-sided polygon, okay? If I find the center of it, okay, GeoGebra will find that center for me, okay? Now it's going to be a little bit difficult with an odd number of vertices here to actually find that center by some of the tools that we have at our disposal right now. But if I draw the circle that starts at H and passes through D, okay, then it also passes through E, F, G, A, B, and C. Does that make sense? That circle is called the circumscribed circle, okay? We're going to need that circle. That circle tells us a lot about the area of this seven-sided figure, okay? Now, H was the center of the circle. It is also the center of the polygon. Is that okay with everybody? Okay. If we use a hexagon, might be able to kind of show some of these relations a little bit better. So a hexagon, the way I find the center of a hexagon is to take some diagonals. Do you agree all the diagonals here are concurrent? They all intersect at one point. For a heptagon, they would not do that. We have to go a little bit further with our process for finding the center. I got G then as my center, and there should be then a circle going from G to D. Does that pass through every vertex? So every polygon has this circle. The center of whatever that circle is what we consider the center of the polygon. Okay. A radius of a regular polygon. Okay. A radius of a regular polygon is the distance from the center to a vertex. Okay. Center of a regular polygon is the distance from the center to a vertex. When we look here, okay, would you guys agree if I start at G and I go to C, come on. Let's do it this way. Let's go. Let me remove that. Oh. Do you guys agree that that distance right there starts at the center of the regular polygon and goes to a vertex? Okay. What are you noticing about the radius of the polygon compared to the radius of the circumscribed circle? They're the same thing. Okay. They are the same thing. And that's kind of a situation that's similar to what we were talking about when we, I don't know if I still have it up. Yeah, right here. When we talked about because a square is a regular polygon, is it not? Okay. So right there, when we created that center and drew that radius, we were drawing the radius of that polygon. Does that make sense to everybody? Okay, which is also the radius of the circle. So, you know, when we stopped doing this problem, we talked about different ways, different formulas that we could have used to find the area of this thing. The formula we introduced to find the area of a hexagon or an octagon or an n-gon, whatever it may be, would also allow us to find the area of a square as well. Okay, because a square classifies as a regular polygon. But that is the radius of our circle. It's the radius of the regular polygon. Okay. A central angle of a regular polygon, the central angle is the angle between two consecutive radii of the regular polygon. So, that right there, so when I say the angle, I'm talking about, go that one to that one. That 60 degrees there is considered a central angle. Is that okay with everybody? The two radii have to be back to back. They have to be going from the center of the polygon to then consecutive vertices. You cannot skip. Like I couldn't draw the radius from G to B, and then the radius from G to D, and consider that a central angle. Okay. Why is that 60 in this situation? How could I find that is 60? What do you know about each of those triangles there in that polygon? Yeah, they're all isosceles, so the radiuses of those are all the same, okay? So if these are the same, okay, and we've got some other stuff going on here as well. This triangle here is actually a regular triangle, and that's unique for a hexagon. But that triangle there is congruent to that one, congruent to that one, congruent to that one, right? So all of these central angles, that central angle there, and this central angle here, and this one there, and that one there, and that one, and that one, they're all the same because of CP, CTC, right? Does that make sense? They're all 60. Now, if I take out the hexagon, okay, so if we don't look at the hexagon, let's hide that. Those slices of that circle should add to 360, correct? Okay. And that connection there, that relationship was actually first understood. It's why we say that there's 360 degrees in a circle. It's first understood by the Babylonians because they knew that there were 60 degrees. They could construct a hexagon, okay, a perfect hexagon, and they knew that angle had to be 60. That angle had to be 60, 60, 60 because they knew the congruency of these triangles. And when they put this circle around it, they say, well, that circle must have to have the same amount of degrees that the hexagon had. Does that kind of make sense? Hexagons are some of our most stable shapes. Okay, triangles are our strongest shape. Okay, if you ever look at a bridge, usually your bridge is going to have a lot of iron bracing that creates triangles. Okay, hexagons create a lot of strength. Okay, and a lot of if you were to keep track of military technology, a lot of the wheels on military trucks, okay, and vehicles actually they're tubeless or airless, because if I'm in combat, what's the easy thing to do to a car? Shoot the wheels, right? Okay. So what they'll do is they'll make the wheel structure out of a bunch of honeycomb hexagons, which becomes very structurally sound. Honeycomb for bees is a very structured. Bees have it just programmed into them that they can make essentially perfect hexagons to maximize area, so they can maximize their honey production. And a hexagon maximizes area. We can fit, because hexagons fit together really nice. Okay, there's no wasted space when we start to honeycomb hexagons together. But that is a central angle. Are we okay with that? Okay, so how did I get 6? So 360 divided by the 6 gave me that 60, right? Okay, so if we had, let's do give me another regular polygon. Let's go 12 sides. Kind of ridiculous here. And find its center. And now I'm going to find, would you guys agree that is one central angle? Okay. There should be how many of those I can fit in there? 12. Okay, so we got essentially a clock here, right? Okay. How big should that angle be? 30 degrees. Okay, 360 divided by the 12 central angles, right? Okay. Is everybody okay with that? So if I look at the clock on the wall up there, okay, that is never right. When the minute hand travels between 7 and 8, it is traveling 30 degrees. Does that make sense? When it goes between the 8 and the 9, it's traveling 30 degrees. What about, so are we seeing that we take to find the central angle? This is going to be something you want to write down. The central angle measurement is equal to 360 divided by n, where n is the number of sides that the polygon has. The next, I think those three, hopefully those three definitions are, once you see them, they're kind of obvious. Okay, they're using some terminology that we've used elsewhere, so we can kind of make the jump to using it here. But this last one you've probably never heard of before. It's called an apothegm. Okay, apothegm. Okay, it's like to be honest with you, I'm not sure what the origin of that word is, but it is the perpendicular distance from the center of the polygon to a side. It says every apothegm of a figure is congruent. Okay, what this apothegm really is, you guys remember back in chapter 4, and I gave you an isosceles triangle, and we found the angle bisector of the isosceles triangle. And the angle bisector of an isosceles triangle is perpendicular to the base, and it cuts the base in half. An apothegm is exactly that for every one of these triangles in here. Okay? So if I go from, let's see here, this segment right there, okay, that red segment is an apothegm of that regular hexagon. Okay? And what it does is it takes that 60 degrees, that was that central angle, which is also if I look at just the triangle, let's look at this triangle here real quick. So many different relationships exist here that we've talked about over the course of the year. If we look at that blue triangle, okay, it's an isosceles triangle, right? Does that make sense to everybody? If we look at that blue triangle, is that blue triangle also isosceles? So all these triangles that are made by looking at the side of your polygon along with the two consecutive radii will always generate isosceles triangles on the inside there for you. Okay? The apothegm is then always going to be the segment that starts at the vertex, okay, or a vertex angle, or the center of the polygon, however you want to view that point right there, and it goes perpendicular to a side. Well, if it goes perpendicular to a side, what does it do to that 60 degrees up there? Bisects it, cuts it in half, right? What's it do to this base down here? What's it do to this side? Bisects it, okay? But that distance, that red distance, is called an apothegm. And every figure has, every regular polygon has n apothegms. Meaning, if I draw all of these segments, that one, that one, that one, and that one, all of those red segments would be what we call apothegms. Okay? Now, they're all going to be the same length. Does that make sense? Okay? How does an apothegm, in regards to its length, compare to the radius of a regular polygon? Is it? So the radius goes, so that radius goes all the way to the circle, right? So if I make a radius that overlaps the apothegm, that'd be that one right there, right? So the radius is longer than the apothegm. Okay with everybody? Okay. Now, something that will become a point of emphasis later on is this little like section, right? This little like white section or clear section. Those are called segments of a circle. But the radius passes through that segment of the circle, and the apothem does not go that far. So the radius is always longer. So I've got here a image that we're going to use consistently to find areas for these figures. And what we're going to do is tomorrow, first thing in class, is we're going to find the area of any one of these shapes by finding the area of these triangles. Okay? You see that little right triangle right there? Can we find the area going 1/2 base times height? We could. Okay? And in that, there would be 12 of those in that problem, right? So I can find the area of any one of these shapes that we do by finding that smallest area of the triangle and then multiplying by how many of those triangles we have. It will work every single time. It's going to be tedious to do that. So we'll take that idea and use some generic values, some variable values to identify apothem, do some kind of reconfiguring algebraically, and we will find a new formula for this that adds all those triangles up by itself without us having to actually physically do that. Does that make sense? So that's going to be the start of class tomorrow. No homework this evening. You guys can go.